This is the Riemann zeta function, drawing its path through the complex plane. Watch the gold circle at the center. Every time the curve threads it perfectly, exactly through the middle, it reveals a secret about the prime numbers. There, and again, mathematicians call these events zeros. They have found 10 trillion of them. Every single one obeys the same hidden rule. Why? Nobody on Earth can prove it. The question is called the Riemann Hypothesis. It has resisted every attack for 165 years, and there is $1 million prize for settling it. This film takes you there in 5 levels, starting from nothing but multiplication. By the end, you will understand exactly what the question asks, and why it may be the deepest one mathematics has ever posed. Level 1. The atoms of arithmetic.
Pick a whole number, say 60. You can break it into smaller pieces that multiply back together, 6 times 10. And those pieces break further. 6 is 2 times 3. 10 is 2 times 5. But now you are stuck. 2, 3, and 5 refuse to split. They are primes, whole numbers whose only divisors are 1 and themselves. Here is the deep part. However you choose to split a number, whatever route you take down the tree, you always land on the same primes at the bottom. Every whole number shatters into primes in exactly one way. Mathematicians call this the fundamental theorem of arithmetic. It is why primes deserve the name atoms. Chemistry has its periodic table. Multiplication has the primes. Everything else is a molecule.
So how do you find the atoms? The oldest method still works beautifully, invented around 240 BC by Eratosthenes, chief librarian of Alexandria.
Keep the first number standing, 2, and cross out all its multiples. Keep 3, cross out its multiples. 5, 7, whatever survives the sieve is prime. Notice something as it runs. The first new crossing for each prime happens at its own square. Everything smaller was already removed, so the sieve finishes faster than you would ever expect. 25 primes survive below 100. But look at them. 89 and 97 are prime. Nothing between them is. The sieve produces the primes without explaining them.
Wait, if they keep thinning out like that, do the primes ever just stop?
Around 300 BC, Euclid of Alexandria settled that question with one of the most admired arguments in all of mathematics. It survives in his own voice, more or less, 23 centuries later.
Suppose you had a complete list of every prime that exists. Humor me. Say it is 2, 3, and 5, and nothing else. Multiply your whole list together. 2 times 3 times 5, 30. This number is divisible by every prime you own. Now, add 1. 31. Try dividing it by each prime on your list.
Every single one leaves remainder 1. 2 doesn't divide it, 3 doesn't, 5 doesn't.
And yet, 31, like every number above 1, must have some prime factor. So a prime exists that your complete list is missing. And notice, the argument cares nothing for which list you chose. Any finite list of primes is incomplete. The primes never end.
Notice what just happened. The proof never named a single new prime. It conjured one out of pure logic. A guarantee covering infinitely many cases at once, something no amount of checking could ever deliver. Hold on to that distinction. It returns with force at the end of this film. Infinitely many primes, then, but scattered how? In 1963, the physicist Stanislaw Ulam, doodling through a dull conference talk, wrote the numbers in a spiral and circled the primes.
1 in the middle, 2 to the right, spiral outward, forever. Light up every prime, and watch. Those diagonal streaks, nobody arranged them. They emerge. Some diagonals are strangely rich in primes, and to this day, nobody has fully explained why.
This is the central tension of our entire journey. Primes look random up close, but lawful from afar. The Riemann hypothesis is the precise statement of how lawful they are. Level 2. Counting the uncountable.
The way out of the paradox is a change of question. Stop asking which numbers are prime. Start asking how many primes there are up to a given point. Individuals are unpredictable. Populations have statistics. Mathematicians write the count as pi of x. Nothing to do with circles. Just the letter p for prime counting. Pi of 10 is 4, 2, 3, 5, 7. Plot it, and you get a staircase, one step up at every prime. Up close, it is all elbows, jerky, irregular, stubbornly local. Now step back. 10,000, 100,000, 1 million.
The steps have fused into a single, confident sweep. Nothing about the primes changed, only your distance from them. The lawlessness is real, and so is the law. Around 1792, a teenage Carl Friedrich Gauss noticed what the law might be. He counted primes in blocks of 1,000, by hand. He later claimed to have counted every prime below 3 million this way.
His observation: near a number x, roughly 1 in every natural log of x numbers is prime. Near 1,000, about 1 number in 7. Near 1 million, about 1 in 14. Multiply x by 10, and the log only grows by about 2.3. The primes thin out, but glacially. If that density is right, then adding it up should predict the count. Gauss's refined estimate does exactly that. It is called the logarithmic integral, written Li of x.
2 candidate laws, 1 truth. Let them race.
Gold is the truth, pi of x. Rose is the first guess, x over log x. Cyan is Gauss's refinement. Watch what happens as x climbs to 1 million. The first guess trails about 8% low. But Gauss's Li hugs the true count so closely you can barely separate the curves. At 1 million, it is off by about 130 primes out of 78,500, an error of 1600ths of 1%.
What the race suggests, a century of work confirmed. In 1896, Jacques Hadamard and Charles de la Vallée-Poussin proved it independently. The proportion of primes near x is exactly 1 over log x. In the long run, it is called the prime number theorem. Pause on how strange this is. No one can tell you whether the next number is prime without checking. Yet the census of primes obeys a law as clean as anything in physics. The atoms are anarchists. The population files tax returns.
But hold on. The theorem says they agree eventually, in the limit. How far apart can they drift along the way? That gap at 1 million was 130. Is the drift ever huge?
That is precisely the right question. The pattern exists. That is settled. The question is no longer whether the primes follow a law. It is, how big is the error term? Hold that thought. It is where the Riemann hypothesis lives. Level 3. The golden key. To attack the error term, mathematics had to leave the whole numbers entirely for an infinite sum that starts somewhere absurdly distant from primes. The simple act of adding fractions forever.
1 plus a half plus a third plus a quarter. The terms shrink towards 0, so you might expect the total to level off. It does not. Group the terms in doubling blocks, and every block is worth more than 1/2. Infinitely many blocks. Half a unit, forever. The sum creeps past every ceiling, absurdly slowly. It needs about 10 to the 43 terms just to reach 100. This is the harmonic series, and its divergence will echo through everything that follows. Now, make one small change. Raise each denominator to a power s. This defines the zeta function. For s equal to 1, it is the harmonic series, infinite. But for any s bigger than 1, the sum settles on a finite value. And those values are astonishing. In 1735, Leonhard Euler computed the value at s equals 2. The reciprocals of the perfect squares add up to pi squared over 6. Add up fractions, pure arithmetic, no circles anywhere, and out falls pi. It was the first hint that this innocent sum is a trapdoor into deep territory.
Then Euler found something better. The zeta function doesn't just produce surprising constants. It knows the primes.
His product formula says, the sum over all whole numbers equals a product over all primes, one factor for each. On the left, smooth analysis, no primes in sight. On the right, nothing but primes. Why would that hold? Because of level 1, each primes factor expands into that primes powers, and when you multiply everything out, every whole number gets manufactured exactly once, because every number factors into primes exactly one way. Watch the numbers light up as we switch each prime on. 2, 3, 5, 7, 11, 13. With every prime, the product climbs closer to zeta. Unique factorization repackaged as an equation. The writer John Derbyshire called this identity the golden key.
Any fact about one side becomes a fact about the other. Euler immediately extracted one. Since the harmonic series diverges, there must be infinitely many primes. Euclid's theorem again, 2,000 years later, from an entirely different direction. The bridge between analysis and the primes was open. Here, Bernhard Riemann enters, in 1859, with a move of pure audacity. Feed the zeta function, not just real numbers, but complex numbers.
If you have never met them, here is the honest 2-minute version. There is a number called I, whose square is -1. A complex number, a plus bi, is simply a point in a plane. A steps east, b steps north. Nothing mystical. They add like arrows and they multiply like rotations. Square a complex number and its angle doubles while its length squares. Multiplication becomes geometry. Why bother? Because well-behaved functions of a complex variable are unreasonably rigid. Knowing one small patch of such a function determines all of it, the way a few bars determine a melody. That rigidity is the machinery Riemann needed. Watch what rigidity does for a simpler series first. 1 plus x squared plus only converges in the window between -1 and 1, but inside that window it equals 1 over 1 minus x, a function that lives almost everywhere. The series is just one window onto a larger creature. Riemann proved zeta behaves the same way. There is a unique function, defined on the entire complex plane except a single point, that agrees with the sum wherever the sum exists. This is analytic continuation, and honesty requires a flag. Actually building it takes real machinery we are waving at, not performing. But the result is ironclad. It also explains a famous piece of internet lore. You may have heard that 1 plus 2 plus 3 plus 4 equals -1/12. Stated like that, it is false. The sum diverges. Full stop. The true statement, the continued zeta function takes the value -1/12 at s equals -1, where the original sum is simply not valid. A category error, with a beautiful truth trapped inside.
So what does the full zeta landscape look like? Here it is, the actual function, every pixel computed. Hue shows direction, brightness shows size. The white blaze at s equals 1 is the pole, the ghost of the harmonic series, the function's one breakdown.
On the negative real axis, dark wells at -2, -4, -6, zeros, places where zeta vanishes. These are fully understood. Mathematicians call them the trivial zeros.
But climb upward into the vertical band between 0 and 1, the critical strip. A new species of dark well appears, floating off the real axis. And look where they sit. 1/2 plus 14.1i, 1/2 plus 21.02i, 1/2 plus 25.01i, all of them dead center on the strip's middle line. Every mystery the zeta function still holds lives with these zeros. Level 4. The critical line.
Two facts frame everything. East of the strip, the golden key keeps zeta from vanishing. A convergent product of non-zero factors cannot be zero. And a mirror symmetry ties the strips east to its west, with the center line, real part 1/2, as the mirror. The strip has a spine, and the symmetry keeps pointing at it.
So, walk the spine, sample zeta along the critical line, and draw the output as a path. Whenever the path passes exactly through 0, we have caught a zero sitting precisely on the line.
The path loops and swings like a compass needle in a storm. And yet, there, dead through the origin, the first zero, at height 14.134725. Again at 21.02, at 25.01, at 30.42, every pass exact, not near the origin, through it.
Riemann computed the first few zeros by hand. With a formula so far ahead of its time it was rediscovered in his private papers 70 years later. He found them all on the line, and then he wrote one of the most consequential sentences in mathematics.
It is very probable that all of the roots are real. One would certainly wish for a rigorous proof here. I have, after some fleeting futile attempts, provisionally set aside the search for one.
In modern language, here is the claim, the Riemann hypothesis. Every non-trivial zero of the zeta function has real part exactly 1/2. In the infinite critical strip, the zeros never stray from the one-dimensional line down its middle. That is the entire statement. 8 words of mathematics and 165 years of silence.
3 things it does not say. It hands you no formula for the next prime. It does not say the zeros are evenly spaced. Their spacing is its own deep story. And it is not about the original sum. The zeros live where only the continued function rules. Without level 3, the statement wouldn't even parse.
Okay, but why should anyone care where some function's zeros sit? What do the zeros have to do with actual prime numbers?
Everything. And this is the payoff of the entire climb. Riemann proved an exact identity, the explicit formula, connecting the prime staircase to the zeros. Not approximately, exactly.
Read it as physics. The primes are a sound. The term x is the fundamental hum, this smooth ramp, and each zero contributes one overtone, a wave, whose frequency is the zero's height on the critical line. Add the first zero's wave, the second, the fifth. You can hear each one enter. The ramp is growing knuckles. 20 zeros, 40. The waves are conspiring, bunching their crests at the primes, canceling in between.
100 zeros, and the smooth hum has sharpened into the exact, jagged staircase of the primes. The randomness of the primes, reassembled from pure tones. The zeros are not bookkeeping. They are the spectrum of the primes, and what you just heard is why this subject is called the music of the primes.
Now the hypothesis snaps into focus. In the wave picture, a zero's real part is a volume knob. A zero at real part beta contributes a wave of size x to the beta. If every zero sits at 1/2, every corrective wave is as quiet as the symmetry allows. Size square root of x. In 1901, von Koch made it exact. The Riemann hypothesis is equivalent to the prime counting error never exceeding essentially square root of x. And square root error has a famous meaning. Flip a fair coin x times, heads minus tails hovers near the square root of x. So the hypothesis says the primes are exactly as fair as a coin flip, random in detail, impeccable in aggregate.
A single stray 0, 1, anywhere off the line would mean a rogue wave, primes conspiring somewhere out there on a scale no one has ever observed. Hundreds of theorems, proved conditionally on the hypothesis, would stand or fall with it. That is what hangs on 8 words. Level 5, where we stand. 165 years of assault. Some highlights. 1896, Hadamard and de la Vallée-Poussin proved the prime number theorem by proving no zeros sit on the strip's outer wall. Riemann's blueprint works. 1914, Hardy proves infinitely many zeros lie on the critical line. It sounds close to the hypothesis. It is not. Infinitely many on the line says nothing about whether any sit off it. 1953, Alan Turing, with one of the first electronic computers and a clever method of his own design. Machine verifies the first 1100 zeros. Computational mathematics is born, checking the Riemann hypothesis. 1974, Levinson proves at least a third of all zeros are on the line. 1989, Conray pushes it past 40%. Powerful, and a measure of the gap. The strongest methods known certify less than half of what the hypothesis claims. 2018, Rogers and Tao prove the de Broglie-Neumann constant is at least 0, meaning if the hypothesis is true, it is true with nothing to spare. No proof can win by a soft estimate. Whatever works must be exact.
Meanwhile, the computers, the first 10 trillion zeros have been checked. Every one sits exactly on the line. Surely that settles it.
No, and number theory has taught this lesson brutally. Remember the race, Gauss's curve running slightly ahead of the truth? It runs ahead in every range ever computed. Yet Littlewood proved the lead changes hands infinitely often. The first crossover may lie beyond 10 to the 300, far past anything we will ever compute. And the Mertens conjecture, verified to billions, strong enough to imply the Riemann hypothesis, was disproved in 1985, without anyone exhibiting a single counterexample. In this subject, the integers we can reach are not a fair sample of the integers that exist.
So belief today rests on a tripod. Unbroken computation, 10 trillion attempts at disproof, all failed. Partial theorems, 40% of zeros provably on the line, almost all provably near it. And a structural coincidence so strange it deserves its own scene. Take the gaps between consecutive zeros and rescale them. In the early 70s, Hugh Montgomery computed their statistics, and over tea at Princeton, the physicist Freeman Dyson recognized his formula instantly. It was the formula for energy levels of heavy atomic nuclei. The zeros repel each other, exactly like the eigenvalues of random matrices from quantum physics. Here are 100 zeros against that quantum prediction. With millions of zeros, the match becomes almost perfect. Nobody fully knows why.
But there is a dream, the Hilbert-Polya conjecture. Eigenvalues of certain operators are automatically real, and all zeros on the line is, after a change of coordinates, precisely the statement that certain numbers are all real. Perhaps the zeros are the vibration frequencies of some undiscovered mathematical object. Find the object, and the hypothesis proves itself. In 2000, the Clay Mathematics Institute named it one of 7 Millennium Prize problems, $1 million for a proof or a disproof. It is the only problem that also headlined Hilbert's famous list a century earlier. Hilbert was asked what he would want to know after sleeping for 500 years. His first question: has the Riemann hypothesis been proven? At the start of this film, you saw the Ulam spiral, and were told its diagonals were a mystery. Look at it once more. You see differently now. The dots are still where they always were, but you now know that behind this scatter stands a smooth law, that the law's fingerprints live in a single function on the complex plane, and that the scatter itself decomposes into waves, 1 per 0, like sound into tones. The deepest open question in mathematics asks only this: are all those waves equally quiet? Riemann thought it very probable. 10 trillion zeros agree with him. Proof is another matter. Perhaps it falls to someone who started, one quiet afternoon, by stepping through a sieve.